This video presents our project on perception and learning for robotics, neural rendering for semantic segmentation. In real-world scenarios, vision applications such as semantic segmentation rely on large-scale data to guarantee generalization capability. However, there is often a domain gap between the training dataset and the data scene in deployment. Therefore, the model's ability to continuously adapt to the new environment is crucial. To adapt to new scenes, one idea is fine-tuning, which trains the network only on the new data. However, its performance on previous scene samples will degrade drastically due to a phenomenon called catastrophic forgetting. To mitigate this problem, we explore continual learning in semantic segmentation, which aims at learning the new knowledge while also preserving the old knowledge in a fully self-supervised manner. But how can the model get new training data from the new environments in a self-supervised way? A key idea is to leverage multi-view consistency, which can help increase the robustness of the semantic labels by enforcing 2D/3D constraints. But how? The first option is mapping, which constructs explicit scene representations such as a voxel grid. But it requires a lot of memory and computation. Inspired by recent progress in neural rendering, we use Nerf in our project to construct a more compact and flexible scene representation, which could generate geometry-consistent views and labels with less memory while maintaining high quality and efficiency. The figure illustrates the idea of integrating neural rendering into the continual learning pipeline. Given the initial data, we first pre-train a semantic segmentation network and predict results from new scenes directly. The initial semantic predictions and RGB images of the new scene are then used to train a semantic Nerf model for each scene individually. Then, the semantic Nerf model could generate view-consistent pseudo-labels. Finally, both data stored in the replay buffer from the old scenes and newly generated data are used to update the model. The replay buffer is also updated for continual learning of the segmentation network on new scenes iteratively. Here shows Cementic Nerf, which uses Nerf to construct both color and semantics. However, it assumes the ground truth semantic label in training. To address the noise presented in predicted labels, we made the following improvements. First, separate semantic networks are trained to disentangle the learning of RGB and density from the noisy semantic labels. Second, inspired by instant, multi-resolution hash encoding is used for both geometry and semantics for faster training and inference. Finally, the model outputs semantic class distribution instead of raw semantic logits to equalize the contributions from each sample point. When it comes to empirical results, our method has greatly outperformed Cementic Nerf in terms of time efficiency with a model size of the same order of magnitude. In terms of segmentation performance, our method has advantages in all metrics, providing better pseudo-labels for the continual learning stage. In the end, we show qualitative results of the ground truth label, the predicted label, the baseline, and our proposed method. We can see that our method can produce more view-consistent labels which also fit each object better, even when the predicted labels are inaccurate. Thanks for your attention.